Hi everybody, welcome back to your regularly scheduled programming. Today we are solving LeetCode 409, which is called the longest palindrome. The problem states, given a string S, which consists of lowercase or uppercase letters, return the length of the longest palindrome that can be built with those letters. Letters are case sensitive. For example, an uppercase K followed by a lowercase a is not considered a palindrome here. It gives us a couple of examples, and it gives us a constraint of the length of S is going to be in between 1 and 2000 inclusive. A palindrome is just a word, phrase, or sequence that reads the same backward as forward. They can be even in length or odd in length. Some examples of odd-length palindromes are race car, mom, radar, or kayak, and some even-length ones are Hannah or Abba. We're asked to return the length of the longest palindrome that can be built with the letters from a string S that's going to be provided for us. Keep in mind we don't need to use all the letters, so our palindrome doesn't have to make use of all the letters in the string S. We can actually omit some of the letters. Let's start with the right hand side. I've constructed a table here with some simple examples. We'll work through them all. On the left hand column I have the string, in the middle I have the palindromes we're going to make, and on the right hand side I have the maximum length. Keep in mind that this isn't an exhaustive list of the palindromes we can construct from the string S. It's just one of the possible max length palindromes we can construct. If we're given a single A, the maximum length we can get is 1, and that's just by using that A. A is read the same forward as it is backwards. If we're given 2 A's, we can use both of them. It's going to be the same forward as it is backwards, and we have a max length of 2. If we're given A and B, we can only use A or B to construct our palindrome. We can't use both because it wouldn't be read the same forward as it is backwards. AB is not equal to BA, so our max length for this one is just 1. If we're given 2 A's and a single B, we can use both of our A's. We'll just split them in half and distribute them on either side of the palindrome, and we'll put our single B right in the middle. So it's just going to be sandwiched in between the even numbered A's. If we're given 2 A's and 2 B's, we can create ABBA or BAAB, where we made use of all of our letters in our string. So our max length is 4. If we're given 2 A's, 2 B's, and a single C, we can use all our A's and B's. So like I said before, we can just divide them in half and place them on either side of the palindrome. So A, B, and BA. And then we can put our single C right in the middle sandwiched, which was the same as in this case here. In our next one, we have a single A, we have 2 B's, and we have 3 C's. So the palindromes you can construct here are B, C, 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 B, or B, C, A, C, B. So let's just start off with our 2 B's. So we know, as I've mentioned previously, we can just split them in half and put them on either side. So I can put my 2 B's on the outside like that. Now for using my A or my 3 C's. So I can either just use my 3 C's, put them right in the middle and omit the A, or I can put my A right in the middle and then use 1 less of my C's. So only use 2 of my 3 C's. Moving on, we have 3 A's, 2 B's, and 5 C's. So let's just start off with my B's, split them in half and put them on either side. Cool. Now the option between the 3 A's or the 5 C's. So I can put my 5 C's in the middle and then use 1 less of my 3 A's and put them on the outsides. So just 2 A's and 5 C's. Or I can use all of my 3 A's and use 1 less of my 5 C's. So I have 4 C's and I put them on either side. And we have a max length of 9 for this one. So we can come up with the following conclusions based on what we've seen in this table. The first one is we're only allowed 1 odd sequence per palindrome, and it goes right in the middle. So as we saw in these last 2 examples where we're given more than 1 odd sequence, so either the single A or the 3 C's or the 3 A's and the 5 C's, we could only use 1 of the odd sequences in our palindrome. The other odd sequence we had to take 1 off of to make it even to use in our palindrome. In this last one, we were able to only use the 5 C's or the 3 A's. The other letter, so for the first one, we had to use 1 less of our 3 A's, and in the second one, we had to use 1 less of our 5 C's. Next is we can use all even sequences. So all even sequences are allowed, and that's what I mentioned earlier with just split them in half and place them on either side of the palindrome. The final thing is we can convert odd sequences to even by using one less. So this is tied into what the problem gave us with we don't need to use all the letters from our string to create our palindrome. In this last example, or in these last two examples, I walked through this one where when we wanted to use our 5 C's, we also wanted to make use of our A's, but we couldn't make use of all of them because we couldn't distribute them evenly to make a palindrome. So we used one less. We converted it to an even count by subtracting 1. Or if we did it the other way around, we used our 3 A's and now we couldn't use our 5 C's, but we can use 4 C's. We can just distribute them as mentioned here. So I'll use these 3 principles in solving this problem now. I'm given 3 A's, 5 B's, 4 C's, and 2 D's. And I've mapped them out here with the letter being the key and the value being the count of the letters. So the first principle, I can just start off with all even sequences are allowed. That's just a simple one, right? So let's just start off with our even sequences. So we have 2 D's. I'm just going to do what I mentioned before where I just put them on either side. Split them in half and put them on the sides. And then I have 4 C's. That's also an even count. So I'm just going to do that same thing. C, C. I probably wrote this too big. So I'm just going to wipe that. Sorry. Have a lot of letters we're working with here. D, D, C, 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 C. Cool. Now we're left with, I'll just put a check mark here to make sure we know that we finished those. Now we're working with our odd numbers, so 3 and 5. We're only allowed one odd sequence per palindrome and it goes in the middle. So we can, as I mentioned above here, when we were doing this last example, we can go either direction. So let's start off with just going with the 5 B's. So I'll put them right in the middle. 5 B's in the middle. And now the other one, the 3 A's can be converted to even by just using one less of them. So if I used one less A, would have 2 A's, and I could just distribute them like that. And now our max length for this is, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Or we could have just done that by calculating from our hash map. So we could have done 4, 2, our 5, and using one less of our 3, so that's just 2. And that's the same thing. So 4 plus 2 is 6, 6 plus 5 is 11, 11 plus 2 is 13. Or we could have done it the other way, where we used the 3 A's instead. So let me just get us back to that same part. So we have all those. And now this time we'll put our 3 A's in the middle. Sorry, I just put a 3 there, got confused. And then we'll use one less of our 5 B's. So we'll use 4 B's. And we can just distribute those like that. And that's going to be the same thing. So if we went that direction, it would just be 4, 2, and then we'd have used 4 B's, and we'd have used 3 A's. And that's the same thing. So 4 plus 2 is 6, 6 plus 4 is 10, 10 plus 3 is 13. So you can see that the strategy works, and this is what we're going to use to implement in our code to help us solve this problem. Here is the code to the hash map solution. We're going to first initialize our variables. We're going to need a map, we're going to need an even count and odd count variable, which are going to represent the sums of the letters that occur an even amount of times and odd number of times respectively, and we'll also need a flag, which we'll see the need for later on. Next, we're going to iterate through S. We're going to store each letter as a key and its value as the frequency of the letter. We do this by checking if the map contains the character already. If it does, then we'll increment the value. Otherwise, we're going to initialize it with 1 in the map. Next, we're going to iterate through the map. If the value is even, which we'll check with this modulo operator, which returns a remainder. So if the value modulo 2 returns a remainder of 0, then we'll know our value is even, and we can increment our even count by that amount. Otherwise, we know it is odd, and since we know that we can use all letters with an even number of occurrences, we can convert our letters with an odd count to even by subtracting 1, which is virtually using 1 less, which we saw on the board. But since we know we can use one odd sequence in our palindrome, we can reclaim one letter we subtracted when converting all the odd sequences to even and use it. we'll reclaim that letter by setting our flag equal to 1 and adding it to the total count. Finally, we'll return our even count plus our odd count plus the flag if it applies. And this total sum is going to yield the maximum length of the longest palindrome we can create. So if I run this, it'll pass our test cases and we can submit it. Great. The time complexity for the hash map method is going to be O of n linear, where n is the length of the input string s. The function has 2 for loops, but both loops iterate through the characters in the string s once. The space complexity of the function is O of k, where k is the number of unique characters in the input string s. In the worst case, where all characters are unique, the space complexity will be O of n linear, as the map could store frequency values for up to n unique characters. In the best case, where all characters in the string are the same, the map size will be 1 and the space complexity will be O of 1 constant. We can also solve this problem using a set. So sets contain only unique elements and contain no duplicates. We're going to iterate through the string, and each time we're going to check if the set has that character. If it does, we're going to increase our count by 2 and delete that character from our set. Otherwise, we're going to add the character. This takes advantage of our odd and even principles as before, because every time we check if the set contains 1, we then delete it and increment our count by 2, thereby using both of those letters in our palindrome. By extension, then, there's always going to be, if there's an odd number of letters, there's always going to be one of those letters remaining in our set. Let's just walk through it so you understand a little bit clearer. So let's start off with A. Initially, this set is empty, so it's not going to have it, so we're going to add it. Let's add an A right there. I'm going to cross them off like that. Next A, it's going to check if it has it. It does. We're going to increment our count by 2. We're at 2 now. And then we're going to delete that character from our set. I'm just going to literally remove it like that. We're done with that. Now we're on the third A. The set doesn't have any A's, so we're going to leave it right there. Now we're on the B's. So does the set have any B's? It doesn't. We're going to add it. Now we're on the second B. Does the set have it? It does. We're going to increment our count by 2. We're at 4 now. Then we're going to delete it. Now we're on the third B. Does the set have any B's? It doesn't. And then we add it. And then now we're on the fourth B. The set does have one, so we're going to increment our count by 2, 6, delete. Finally, we're on the fifth B. Does the set have any B's? It doesn't. We add it. Cool. Now we're on the C's. So does the set have any C's? It doesn't. Let's add it. Second C. Does the set have a C? It does. Let's increment our count. We're at 8 now, and we're going to delete our C. We're on the third C. The set doesn't have one. We add it. We're on the fourth C. The set has one. We increase our count by 2, 10, and delete. Now we're on the two D's. The set doesn't have a D. We add it. Now we're on the second D. The set does have it, so we increase our count by 2, and we delete our D. So by the end, you can see that we have two elements in our set, an A and a B, and those are both odd counted sequences. So we had 3 A's and 5 B's. The whole principle that this set operates on is that it's going to use only the even numbered letters in our final solution, and that's what this count has incremented this whole time. This is only using the an even number of letters. So we've just subtracted 1 basically from all of our odd solutions or odd sequences, and we've used no odd sequences in our palindrome. We've converted them all to even. But we know from before that 1 odd sequence is allowed per palindrome, and it can go right in the middle. So this set is actually containing 1 more than we actually need. So we can add 1 letter back and use one of those odds in our count, and that's going to increase our count by 1 and thereby giving us a longer palindrome. Because if you remember before, we could have used either 3 A's or 5 B's, but we couldn't use both. If we wanted to use the 3 A's, we'd have to use 4 B's, or if we wanted to use the 5 B's, then we'd have to use 2 A's. So we can do that same principle here. Here we've only used 2 A's and 4 B's because we've kept one in here. So we can give back any one of them and just add 1 to our count if there is something left in the set by the end of it. So we just return 12 plus 1, and this 1 is only conditional on if there's items remaining in the set, because that'll have meant that we didn't use any odd sequences in our palindrome, and we could have. So we'll have to add that in the code. And that's equal to 13, which is the same as what we had before. Here is the code for our set solution. We'll initialize our set and a count variable. Next, we'll iterate through the string, and we'll check if the set contains that character. If it does, we'll increment our count by 2 and then delete that character from the set. Otherwise, the set doesn't contain the character and we'll have to add it. In the end, we'll return the count plus what's going to return from this ternary or conditional operator in JavaScript. And all this is doing is it's checking if the set has a size greater than 0, meaning if there is any items remaining in the set. If there is, then we'll return 1. Otherwise, we're going to return 0. You can run this, and then we can submit it. Cool. The time complexity for the set solution is going to be O of n linear, where n is the size of the input string. The function iterates through each character in the input string once because we have a for loop. The space complexity is O of k, where k is the number of unique characters in the input string s. Space depends on the number of unique characters in the input string. In the worst case, where all characters are unique, the space complexity will be O of n, as that set could store up to n unique characters. In the best case, where all characters in this string are the same, the set size will be 1, and the space complexity will be O of 1 constant.